Hey there, and welcome! Have you ever stopped to wonder how you can stream a movie from a server that's like thousands of miles away, and it happens almost instantly? Well, the answer isn't magic. It's actually light, traveling through these impossibly thin strands of glass. Today, we're going to pull back the curtain on fiber optics, the invisible tech that pretty much powers our entire high-speed world.
All right, let's just jump right in with the big question, the one that started it all. How in the world do we send information across cities, across countries, and, yeah, even across entire oceans at the speed of light? The answer is hiding inside a special kind of cable that has become the absolute backbone of modern communication.
So here's our game plan. First, we'll cover the basics. What even is fiber? Then we'll look at how light zips through it. After that, we'll compare the two main types, weigh the good against the bad, and finally, we'll see how you actually plug these amazing things in. Sound good? Let's do it. Okay, section 1. What exactly is a fiber optic cable? To really get why it's so powerful, you kind of have to forget everything you think you know about regular old wires. We're talking about sending data in a completely different way. See, unlike your standard copper cables that push electricity through metal, fiber optics sends information using little pulses of light. So think about it this way. Instead of electrons just kind of trudging along through a wire, we have photons, actual particles of light, zipping through a tiny, tiny strand of super pure glass. And that one simple change, from electricity to light, is what gives fiber all of its incredible superpowers. And that brings us to its main superpower. Because it's using light, not electricity, fiber optic cable is totally 100% immune to what we call EMI and RFI. That's electromagnetic and radio frequency interference. You could literally run a fiber cable right down an elevator shaft next to all those huge, noisy motors, and the signal would stay perfectly clean. If you tried that with a copper cable, oh man, all that electrical noise would just turn your data into a completely garbled mess. All right, so how do you keep a beam of light trapped inside this tiny, flexible strand of glass, right? How does it not just leak out? Well, the secret isn't just in the glass itself, but in the layers that are wrapped around it. So, at the very, very center of it all, you have the core. This is the super thin highway that the light actually travels down. It can be made of glass, which is amazing for sending signals over huge distances, or it can be plastic, which is a bit cheaper and more flexible, perfect for shorter runs. Now, wrapping that core is another layer of glass or plastic, and it's called the cladding. And this part, right here, is absolutely critical. You can think of it as the guardrail for our little light highway. Its entire job is to keep that light signal from ever escaping the core. So how does it work? Well, the magic is this principle called total internal reflection. You see, the cladding has a different refractive index than the core. And if you've ever seen a straw that looks bent in a glass of water, you've seen refraction in action. The cladding is specially engineered to bend light so perfectly that when the signal hits it, it doesn't escape. Nope, it reflects right back into the core, basically creating this perfect, continuous mirror that guides the light along its path for miles and miles. Pretty clever, huh? So, if you put it all together, you can see the whole anatomy of the cable. You've got the core and the cladding right there in the middle. Then surrounding them is a plastic buffer for a little extra protection, an armor layer, often made of super tough Kevlar for strength, and finally a durable outer sheath or jacket. All of these layers exist for just one reason: to protect that delicate, hair-thin strand of glass that's doing all the heavy lifting. Okay, so now that we know how it's built, let's talk about the different kinds, because it turns out not all fiber is created equal. The two main categories you'll hear about are single mode and multimode, and they're designed for very, very different jobs. And the difference really is all about the path the light takes. Single mode fiber, or SMF, has this incredibly tiny core that only allows one single direct path for light to travel, kind of like a laser beam. This lets the signal travel for insane distances. We're talking over 40 kilometers, which makes it perfect for connecting whole cities or different buildings. Then you have multimode fiber, or MMF. It has a larger core that allows light to bounce along in multiple paths at once. This limits its distance to under 3,000 feet, so you're almost always going to find this stuff running inside a single building, connecting a local network. So fiber sounds pretty amazing, right? And it is, but it's not always the perfect tool for every single job. Like any technology out there, it comes with its own set of trade-offs. Let's just break it down. On the pro side, you get that total immunity to electrical noise, and you can send data over just incredible distances. Can't beat that. But the downsides are pretty real. Fiber is more expensive than standard copper cable. It's also way more delicate to install. You can't just yank it and bend it around a tight corner. And if it breaks, fixing it requires some very specialized and very expensive equipment. And finally, let's talk about how we actually plug these things in. I mean, you can't just stick a bare strand of glass into a network switch, right? You need these specialized connectors on the end of the cable. First step is a real classic, the straight tip or ST connector. You'll often see these in what we call wide area networks, connecting different buildings or campuses, where having a rock-solid, reliable connection is just absolutely critical. Its defining feature is this really secure bayonet-style lock. You push it in and give it a little twist, and it locks firmly into place. That positive lock means it's not going to get accidentally pulled out, which, of course, is why it's so popular for those critical, long-distance single-mode connections. Next up is another super common one, the subscriber connector, or SC. Now, if the ST connector is all about being super secure, the SC is more about speed and simplicity, which is why you tend to see it in different places. You'll often hear installers call this one Square Charlie because of its distinct square shape. And unlike the ST's twist lock, the SC is a dead simple push-on, pull-off connector. Super quick and easy to use. It's most popular with multimode fiber inside buildings, although its bigger size means it is slowly getting replaced by newer, smaller designs. So, when you step back and think about it, from the massive cables lying on the ocean floor that connect entire continents, all the way down to the wiring closet in your local office building, these tiny little strands of glass form the silent, invisible backbone that carries nearly all of our digital lives. It's an incredibly powerful and resilient system, for sure. But that leaves us with one final thought. As our world becomes more and more dependent on this technology every single day, what happens when that fragile glass backbone inevitably breaks? I mean, what does it take to find and repair a cable that's been severed at the bottom of the ocean? Something to think about. Thanks for tuning into this explainer.